So this of what probably will be a set of videos is about the nucleus. AP Chem doesn't require you to know a lot of nuclear chemistry, but knowing the basics is going to help with a few things especially in terms of nuclear stability. If you remember from first year, nuclear chemistry results because there are some isotopes that are just unstable. All the mass is found in a very small space of an atom. And so that can lead to a lot of instability. Nuclei can either be naturally unstable, which is what we focused on mostly during first year, or it can be man-made, unstable, by way of a couple other types of reactions. At some point, every unstable isotope is going to try to become more stable. And when it does, it will eject particles of some sort from the nucleus as the nucleus tries to stabilize itself. And it's these particles that are actually responsible for the radiation that is dangerous. It's not the atom itself that's dangerous, it's the particles that result from the nuclear decay of the unstable nucleus that is the danger. Because these particles are high energy and ionizing particles, they can do a lot of damage. They not only rip electrons out of the electron cloud of molecules that they collide with, but they can break molecules apart. So you can imagine if you have a whole lot of these particles aimed at a person, and that person's cells get a lot of breakage, they are going to be in trouble. And could possibly die. So we're going to focus on 6 different types, or introduce you to 6 different types of particles. Give you a little information about each of them. Alpha particles, the Greek letter alpha, are positively charged particles. Those are what Rutherford actually used to figure out that there was a very small, very dense, very positively charged nucleus in the atom. Alpha particles are actually helium nuclei. They contain 2 protons and 2 neutrons, but there are no electrons, so they are just the nucleus of a helium. Isotopic notation can be shown using either the alpha symbol or He for helium. And notice that isotopic notation, mass of 4 because you have 2 protons and 2 neutrons, but atomic number of 2 because there's only 2 protons. Now, when we talk about nuclear particles, this number at the bottom is typically the amount of positive charge, because you're going to see, actually even in the next particle, that not everything has a positive number down there. So a beta particle is actually a negatively charged particle. And those are what Thomson and other people used when they used cathode ray tubes. And beta particles are actually high energy electrons. So now you're saying, wait, electrons getting ejected from the nucleus. How does that work? Well, good question. We're going to cover that. So isotopic notation for beta particle can either be 0, -1, because again, it's not positive, it's negative, and E for electron, or B- for the beta particle. How do you get beta particles out of the nucleus? It results from the breakdown of a neutron that is inside the nucleus. Maybe at some point you learned along the line that protons, neutrons, and electrons are not the smallest piece of matter that exists. They are actually comprised of smaller things called quarks. And so it's the rearranging of the quarks inside one of the protons, neutrons, or electrons that in part causes the breakdown of the nucleus. So what's going to happen is when a beta particle gets ejected, you have the breakdown of a neutron. So with a neutron, you've got no charge, but a mass of 1. So when it breaks down, it's going to split up into a proton and an electron. All the mass and the positive charge will go to the proton, and then the negative charge goes to the beta particle. All right, there's also something called a positron, which if you notice is also a beta symbol, but with a plus. That's because it is a particle that has the same mass as an electron, but a positive charge. So a lot of people refer to it as a positive electron. Isotopic notation, whoops, that should be a plus there, not a minus. That should be a plus. Isotopic notation looks something like this: beta plus as opposed to beta minus, or E plus 1. Once again, change that in your notes. Positrons result from the breakdown of a proton. So the electron, the beta particle, comes from a neutron rearranging. The positron comes from a proton rearranging. So what happens, you take a proton, put all the mass into the neutron, and then the positive charge is what gets ejected as the positron. You can also have a gamma ray ejected. Notice that we're calling it a ray and not a particle because gamma is a wave of energy. No charge, no mass, discovered by a couple of various people, the Curies, the Becquerels. And remember that it is just a wave of energy. There's no mass to it. So its isotopic notation looks like that. Two other particles that can be ejected from the nucleus include a proton or a neutron. I didn't really list this here, but you can also get just a straight up neutron ejection or a straight up proton ejection. All right, so why is the nucleus not stable? If you remember, there are four fundamental forces. Two of them are what helps hold the nucleus together. So you have something called a strong force, which is the attractive force that is very strong, but only for a short distance. That's what holds the protons and the neutrons together. You also have the electromagnetic force, which is the force between charged particles. In this case, the only thing in the nucleus are the protons, so it's a repulsive force. So you really have a competition between these two in the nucleus. The strong force is trying to hold everything together, and the electromagnetic force is actually trying to blow it apart. So as the atom gets bigger, or as the nucleus gets bigger, you have a weakening of the strong force, and you have a strengthening of the repulsive electromagnetic force because the nucleus is getting larger, more particles overall, plus more positive particles to cause that repulsion. So this is why as the nucleus gets bigger, as the atom gets bigger, you wind up with more and more unstable particles as opposed to stable ones. Okay, couple different reactions we're going to take a look at. We'll probably get through this first one before we'll have to flip to a new video. So spontaneous say that again. Spontaneous radioactive decay is actually a natural process. It's where unstable nuclei that occur naturally will just automatically undergo changes in the nucleus in order to become stable. So there's nothing we can do to encourage spontaneous radioactive decay. That's why it's spontaneous. Almost every element has at least one radioactive isotope naturally occurring. And so when this naturally occurring radioisotope tries to become stable, it spontaneously ejects some sort of particle from the nucleus. It can eject one particle, it can eject a combination of particles, but whatever happens, the idea is these particles get kicked out in order to try and make the atom more stable. It is impossible to predict when an unstable nuclei is going to decay, and that's where the idea of half-life comes in. So spontaneous decay could be an alpha particle, and just really quickly as a review of the math, remember that the masses all have to equal out and the charge all has to equal out. So if something's undergoing a alpha decay, you are going to drop down by a mass of 2 and down by a mass of 4 and a charge of 2. So we would wind up with going from Ra to Rn. Notice that the masses have to add up appropriately. Beta decay, notice up here with the alpha particle we jump down 2. With beta decay you actually have to move up, because 61 plus 1 equals what? To do the math, you actually have to go one step up on the periodic table. So a beta decay results in another proton being generated. And so you actually go up 1 on the periodic table. And then gamma decay, pretty easy. Math-wise, not too hard to do. So really we're just getting extra energy out of the nucleus, but we're not changing the isotope at all. So the AP exam no longer wants you to worry about balancing these guys. So we're going to do a couple and that's it. I think you have just a couple questions to do for homework. But that's the idea. The mass has to equal out on both sides of the arrow and the charge has to equal out on both sides of the arrow. All right, so let's talk about this decay. Remember that it is impossible to predict when an atom is going to decay. But it is easy to predict the rate of decay for different nuclei. If you have a particular atom, you can predict or you can figure out what's referred to as the half-life. The half-life is, by definition, the amount of time it takes 50% of your material to spontaneously decay. So for half-life, it is a first-order reaction, which is going to come back to you when we start talking about kinetics. It's a first-order reaction represented by this equation typically. So you have n sub t, the amount of radioactive particles you have at time t. N sub 0 is how much you started with, and t to the 1/2 is the half-life. So much time, I start with this amount, so much time goes by, and I wind up with this amount. That's basically what this equation is letting you do. This negative 0.693 is the result of the negative 0.693 is the natural log of 1/2. So that's where that comes in. All right, so using that equation, again, we're not going to get too bogged down over it. Using that equation, how long will it take 20 grams of an isotope with a half-life of 35 days to decay to 4.25 grams? Well, we know what n sub t is, we know what n sub 0 is, we know what the half-life is. What don't we know is t. So here's our equation. You can use the solve function on your calculator to figure this out. So there's no need for you to rearrange the equation and isolate the variable and stuff. With the natural log, solve function's a lot nicer. Little more complicated example. This is one that you're going to see a couple of examples of in the book that you, the problems that you do from the book. So take a look at this question. So the half-life for the process of uranium-238 to lead-206 is 4.5 times 10 to the 9 years. Okay, now this result is not just one decay. This is a result of a big, long sequence of decays, ultimately leading to finally the stable substance of lead. So uranium-238 doesn't immediately decay to lead. It goes through a series of decays, and that series of decays takes this much time. So let's say that you have a mineral sample that contains 75 grams of magnesium, 75 milligrams of uranium, and 18 milligrams of lead. How old is that mineral? So using this equation, we want to solve for t. And again, here I rearranged the equation before I decided to let you guys use the half-life. But what we got to figure out is we know how much uranium we have at time t. We know what the half-life is, but we don't quite know how much we started with. So we know we have this right now. So to figure out how much we started with, we've got to kind of backtrack a little bit. That's what this question is letting us do. So the mass ratio, all of the uranium, we want to know how much uranium caused 18 milligrams of lead to form. So that's what this little calculation actually is. It's the not molar ratio, it's the mass ratio of the two elements. So 18 milligrams of lead, which decayed from uranium, you're going to use this. Again, this is just a molar mass ratio in order to figure out how many milligrams of lead you actually have. So 75 plus the amount of lead or the amount of uranium that created